All right, so we are going to try and talk our way through 5.1, number 4, which first things first is to verify that a couple of things solve this differential equation A. So, um, first things first, how do I verify that y1 is 1 over x minus 1 solves some differential equation? What do I need to do?
Differentiate it.
Yeah, take a couple derivatives, toss them in there. All right, so I'm going to say y1 is x minus 1 to the minus 1 power. And that makes y1 prime minus 1 times x minus 1 to the minus 2. And then what else should I be thinking about there? What's the other consideration? How about the chain rule?
Well, I don't think you have to consider the chain rule because the derivative of the inside function is 1.
Okay, good. Yeah, so you always have to consider at least the chain rule, but in this case, I don't have to write it down. Okay, so then, oops, not y2 double prime, but y1 double prime is going to give me 2 times x minus 1 to the minus 3. And then I need to check and see if this thing works. So I'm going to take my differential equation here. Here. It's really going to be this part. So I'm going to take star and evaluate at y1. So I'm going to get that becomes x squared minus 1 times 2 times x minus 1 to the minus 3 plus 4x times negative 1 times x minus 1 to the negative 2 plus 2 times x minus 1 to the minus 1. Okay. Right now, I don't really see a lot of hope that this will kind of magic cancel on me, but maybe it will. What the hell? Let's check it out. So what can you tell me about x squared minus 1?
It's a difference of, it's a difference of linear factors. So yeah.
Perfect. It's a difference of squares. So I can factor that into x plus 1 and x minus 1. I kept that 2 on top. Then I have 3 of these x minus 1s chilling down here. And then here I have a minus 4x over top of an x minus 1 squared. And here I have a 2 over an x minus 1. All right, now what?
You can cancel an x minus 1 on the left side.
Okay, we can whack one of these guys.
And
so
you can combine the left two.
Combine the left two. Right, yeah. I'm going to need a common bottom for this last term, right?
Right.
So what does that last term need to get to the common bottom of everything else?
It needs to be multiplied by x minus 1.
Perfect. So we're going to multiply that one by x minus 1 on the bottom, multiply it by x minus 1 on the top. All told here, I'm going to get everything's going to be over x minus 1 squareds. Get with me on that? And then on the bottom, we're going to have, on the top rather, we're going to have a 2x plus 2, a minus 4x, and a plus 2x minus 2. And then I might notice, let's see, 2's cancel, 2x's and 4x cancel. This gives me a hard 0. Pretty good with that?
Yep.
Okay. So that's why 1 solves. Okay, so then I should go through the same thing with y2.
I have a question.
Yes, sir.
What what technique do you use to determine whether you're going to use a linear combination of the terms to verify validity, or if you're going to do them both individually? Because you get the same thing regardless of whether you do either one, but the linear combination is way more difficult to solve in this case.
Yeah, it's going to be way more annoying. There's a principle called superposition that we're going to get to as we kind of continue forward here. And this is going to say that if y1 and y2 solve a homogeneous ODE, and yp solves the non-homogeneous ODE, then a general solution is cy1 plus dy2 plus yp for c and d arbitrary constants. I guess in maybe good keeping with the rest of the book, I've maybe phrased this as c1 and c2. Yes. So this is kind of what I'm leaning towards. And I'm never going to check that a linear combination solves unless it's really simple. If it's like cx plus d, then I might run it through together. But normally I'm going to pick one, I'm going to work with one, I'm going to pick the other one, I'm going to work with that one, and then I'm going to trust that when I add them together with constants, I'm going to get a solution still.
Okay, because I've been doing linear combinations up to this point, and they've been pretty simple. They've all canceled automatically. The differentiation is sometimes kind of mean, but they do cancel. But this one did not.
Yeah, in this case, you have an awful lot of fractional algebra to be doing in order to get that to work, and it's gonna be nasty.
And I did run it through like a computerized algebra simplification tool, and it did come out to 0 over a whole bunch of terms, but it would have been hell to simplify.
Yeah, and that's true in general. Once once y1 and y2 are a little bit complicated, then plugging them in as as cy1 plus cy2 is going to be a disaster. All right, so do we trust that the other one would work?
Yeah.
So the other one's going to really just be different by a plus sign, but otherwise everything's going to cancel in basically the same way. Okay, so then we're talking one. Why do I see these intervals?
So you've got fractions, and the solutions are going to be undefined for some values.
Yeah, really, I'm kind of seeing that 1 is going to cause problems with y1, and -1 is going to cause problems with y2. And so if I'm hoping for a general solution, the best I can do is someplace where both of them are going to work. Is that kind of jive?
Mm-hmm.
Okay, so do I need to do part B where we solve the initial value problem? We can.
No, we can skip that. What does it mean by what is the general solution of A?
So this is. Oh, what is the general solution of A? So the general solution of A on each of these parts is this thing that I was talking about. It's y is c1 y1 plus c2 y2.
I kind of figured, but I wanted to make sure.
Yep. And then the thing that determines which interval it's valid on is where the initial condition is.
Mm-hmm.
Right. So when we're looking at this one where we have an initial condition that's set up at 0, this one's only going to work on that -1 to 1 interval.
Oh, gotcha, because anything outside of that is going to be invalid because the initial condition's within that interval.
Yeah, in order for me to get over there, right, I'm going to have to step over one of the asymptotes for one of my solutions, and that's not going to work. Like, stepping over asymptotes isn't going to happen. That would be a little bit like, if you're thinking about this differential equation as modeling like the salinity of water in a tank or something, that's a little bit like saying, well, the tank overflows at time 2, but at time 3, the solution is still, and you're like, no, it's not going to work. You stepped over, like something broke there. That's what that asymptote represents.
Mm-hmm.
All right. And then to graph the solution, we would need to find the solution. You can just, go ahead and use Wolfram plot to do that. And then in order to verify Abel's, we kind of need to go find the Wronskian first, right?
Yeah, I tried this and I got an answer, but I'm not entirely sure I fully understand how the Abel's formula works. So,
Okay, so let me pull it in. Okay, so I'm looking at this theorem out of the book, and I'm looking at some words that are defined further down this page. So those words are that this thing is called the Wronskian. And then the other thing is that formula 5.1.29, this object here is called Abel's formula. Okay, so if I'm trying to figure out the Wronskian, right, there are two methods I can use to calculate that. One is the direct calculation between the two things, and the other is this Abel's formula method, which is this kind of W is defined in terms of this integral, right?
Mhm.
So let me see if I can fit the differential equation that I'm talking about into this thing. So let me dump that crap. I just need to grab this guy and scoot. Come here. Come here, little fella. Just walk yourself down here. Okay, so here's the formula, or here's the problem I'm looking at, right? So I just need to kind of think about, all right, what's P going to be? And do we want to do the direct calculation first, or do we want to do the Abel's formula side of it? We need both to verify Abel's.
In order to get W of x naught, don't you need to do the first one first?
Fair. Okay. Yeah. So let's calculate the Wronskian. So let's double check here. The Wronskian is going to be y1, so that's going to be 1 over x minus 1, times y2 prime is going to be 1 over x plus 1 prime. And then I need minus y1 prime. Oh, that's kind of crummy notation. Times 1 over x plus 1. What am I missing here? Oh, code. Okay, so these little symbols were supposed to be primes. Okay, so let's go ahead and plug those in. So we're going to get a 1 over x minus 1, and then this thing's derivative is going to be a what?
negative 1 over x plus 1 squared.
Yeah. So I need a negative 1, and then that thing's squared. And then I need a minus, and I've got a, negative again, x minus 1 squared, and then I have a times 1 over x plus 1 again. Okay, so let's see. Those are going to make this a plus. So all told here, I have a, I don't really have a common bottom here. If we want to feed these together and make things a little bit easier, I'm going to make a common bottom. So I'm going to multiply this by x plus 1 on top and bottom. And I'm going to multiply this by x minus 1 top and bottom. So now I've got this over x minus 1 squared times x plus 1 squared. And then on the top here, I've got a, looks like negative x plus 1. And then on the right-hand side here, I have an x plus 1. Okay, so the x's are going to drop out. And all told here, I have 1 over x squared minus 1 squared.
And it'd be 2 over x plus?
Yes, and it would be 2 because 1 plus 1 is still 2, despite all my years of effort to make it otherwise. All right. Okay, so Then one thing I can notice from here, does this function, right, this w of x, does this have any zeros on any interval whatsoever?
Yeah.
Nope. What does that mean? And this is maybe the takeaway that I want you for sure to have from Wronskian's.
Oh,
So-
crap. There's something about this that I'm trying to remember. It has something to do with. Well, that's it. It either has to have 1 0 or it has to be 0 the entire time, doesn't it?
Yeah, so this is
Or no zeros
this
are
is
all
one
zeros.
spot where the two courses kind of kiss and diverge. So in the linear algebra side, we've been thinking about determinants equal to 0, right?
Mhm.
And that implies that a matrix is singular.
Oh, that's right. The
In this-
Wronskian can be represented as a matrix, can't it?
Yeah. So in this case, what we're seeing here is that if the Wronskian is 0, what that means is that the functions were linearly dependent, and you don't actually have two solutions, you only have one. That would be bad because then I can't solve initial value problems. Does that make sense?
Mm-hmm.
However, in this case, I've found a Wronskian that has no zeros, ergo, my solutions are linearly independent, then I can use them as a general solution to solve initial value problems. I kind of took that for granted in doing the first couple steps, but this is just nice verification for me that that's true.
Yeah. Oh, you're right. Yeah. The function doesn't have any zeros. It has a point at which it's undefined, but
Sure.
no zeros.
Yeah, in fact, 2 points where it's undefined, right?
Mm-hmm.
Okay, so now in order to kind of verify Abel's, I'm looking at this function here. That's w of x, right? And I'm wondering, is that equal to this thing? Well, like, okay, so I'm supposed to let x not be any point. I'm gonna go ahead and set this thing aside as a constant, just quick. I'm just gonna kind of set that aside, and I'm just gonna fiddle with this integral up here. You guys with me on that? So I'm going to, in considering Abel's, I'm just going to consider, and I'm actually even going to drop the minus sign. I'm just going to consider this piece. So we're going to integrate from x naught to 0, and I need p of t dt here. Now, where the hell did p come from?
It's your leading function on y prime.
Okay, good. It's the leading function on y prime. However, is this like, I need this to be the same as this, right? I need these two differential equations to be in the same form.
And it's
they?
not.
No. Shit. How do I make them in the same form?
Divide it by the leading function on y double prime.
Okay, good. So my p function, right? P of x in this case is 4x over x squared minus 1. And then here the kind of interesting thing you might notice, x squared minus 1 has problems, right?
Mm-hmm.
At minus 1 and 1. Notice that p and q are supposed to be continuous, right? So the problems are exactly where it's not continuous. Those are exactly, again, these holes in between my intervals. Right? Those are where p and q were discontinuous. Does that make sense?
Mm-hmm.
Okay. All right. So
in this
now
case,
that
we're taking
figured-
AB to be -1 and 1.
Yeah, we could take AB to be -1 and 1. We could take AB to be 1 and infinity. We could take AB to be -infinity and -1. Any of the three intervals would be fine. Does that kind of jive?
Mhm.
I'm going to probably tend to take x naught to be 0 and look at that middle thing, only because the problem above asked for an initial condition of 0 anyways. But I'm kind of not doing that right here explicitly because I do want to do this a little bit more generally. Does that make sense?
Mhm.
Okay. So now my integral that I'm considering for Abel's, right? So I have kind of Wronskian on this side and Abel's over here. So in order to do Abel's, I've got my integral set up. So that needs to be the integral from x naught to x of 1 over, and then I need to go get my function p. Oh, whoops. My function p doesn't have a 1 over. My function p has a 4t on the top, and on the bottom it has a t squared minus 1, and I need a dt integral here. Pretty good with this?
Mhm.
All right, now how the hell do you integrate this sucker?
I kind of just integrated it by inspection, but technically you'd need to use substitution.
Yeah, okay, good. So I'm going to tend to do u substitution because I'm too dumb to get them right. So u is t squared minus 1. So then d is 2t dt. So I have that. I have a t. I need half of this 4. So I'm underlining half of it, which is probably hard to see. Okay, so I'm now going to have the integral from t is x naught to t is x of, let's see, I got a 2 out front, and then I think I have, oh, we can actually, what the hell? So then I have a 1 over u du. Okay, so we actually do this. We get 2, and then we get, let's see, what's the integral of 1 over u?
Log of u.
Log of the absolute value of the stuff, which in this case was t squared minus 1. And then I need to evaluate from x naught to x. So all told here, I got 2 natural log absolute value of x squared minus 1 minus 2 natural log absolute value of x naught squared minus 1. Good with that?
Mhm.
Okay, now what do I do with that?
Simplify it into one logarithm.
Okay, sure. So this is going to be a, let's see, so I factor 2 out, and then I have a log of some differences. So that's log of the absolute value like this. Maybe?
Looks good to me.
Okay. Then what?
I know what it did.
I guess we can pull this 2 up top.
Yep, that's what I did.
I'm not sure this is a great idea, but we can do it, so what the hell? And that'll take care of my square, or that'll take care of my absolute value as well. Okay. Now I got this horrible thing. Where did this come from? Remember, that horrible thing was actually this integral, right? So I've just done this top piece. I need to actually punch that into the rest of this. Right, so I've got some constant, and then I've got e raised to negative this stuff. Okay, so let's see. So our check, the thing we're supposed to be checking right now, is that the Wronskian side, so 2 over x squared minus 1 squared, and I'm wondering, is that equal to w at x naught times e to the minus natural log of this whole business? Okay. This feels real weird. How do I check this?
You can, first of all, get rid of the e. with
Okay,
the
so
exponent.
I really want to slash that e and that log out. What do I need there? One thing in the way.
You need to move the negative to the exponent.
Yeah, this negative's got to go up in the exponent there. So I should end up wondering, is 2 over x minus 1 squared, is that equal to w at x naught times, let's see, so the e and the natural log cancel out. This whole thing may as well flip over. So I've got x naught squared minus 1 squared over x squared minus 1 squared. You guys with me on that? So with that negative exponent, I just flipped that whole fraction over. Huh. Is that true?
Depends on what the wx naught is, isn't it?
Well, yeah, it kind of does, but what's w?
It's the Wronskian itself.
Uh-huh. So w at x naught should be this function over here, evaluated at x naught, right?
Mm-hmm.
Which is going to end up being 2.
So if I plug that in, this function evaluated at x naught is 2 over x naught squared minus 1 squared. So that's w at x naught. And then I'm multiplying by x naught squared minus 1 squared over x squared minus 1 squared. Notice these guys cancel. Oh, shit, I guess Abel's formula works. That's kind of cool. And what's kind of the point of Abel's formula? Well, the point of Abel's formula is like, yo, dude, look, the Wronskian somewhere is going to be the Wronskian anywhere is the Wronskian at any particular somewhere times this positive quantity. Okay, see that? Like this quantity here is strictly positive, not zero, strictly positive. So what this means is that if the W, right, if the Wronskian has some zero, then it's always zero. If it doesn't have a zero, then it's never zero. It's real weird.
I was gonna ask, like, what's the use for this besides in one of the problems where you use it to find the second solution to a problem?
Oh, what's the use of Abel's formula?
Yeah, outside.
Yeah, Abel's formula is this cool thing that lets you see that it's not just like, it feels dumb to check if the Wronskian has a zero, but the neat thing is if the Wronskian has a zero, then it's always zero.
Mhm.
And that ties kind of nicely into our linear algebra. Like, it's going to take a little bit to get to kind of function spaces and talk about this, talk about why there's a determinant here. But there's a determinant here, and that means that there's a non-invertible matrix going on. So in this case, I have linear dependence if the Wronskian is zero. And if it's not zero, then I'm scot-free and I can use both solutions. And that's primarily what we're going to use it for. Does that sort of make sense?
Mm-hmm.